Hi all, welcome back to my channel. I am A. Sindhu Devi, Assistant Professor in the Department of Computer Science and Business System, working in Jerusalem College of Engineering. We can move into the video now.
Welcome. Today, we're diving into memory and input-output systems, the backbone of how computers store data and communicate with the outside world. This session, part of Unit 5, will explore key concepts that keep our devices running smoothly. Let's get started with the fundamentals behind memory and I/O operations. Virtual memory is a clever way computers handle programs that are bigger than the physical RAM they have. Instead of loading the entire program at once, only the parts needed right now stay in RAM. The rest gets stored safely on secondary storage, like an SSD or hard drive. This lets the computer run large programs smoothly, even when memory is limited. It's a smart balancing act between speed and capacity. Let's talk about virtual memory. Imagine you have just 4 gigabytes of RAM, but your program needs 10. Clearly, it won't fit all at once. That's where virtual memory steps in. The operating system swaps pieces of the program in and out of RAM, using secondary storage to hold the rest. This lets us run programs larger than the physical memory available, making our computers more flexible and powerful. So, why do we need virtual memory? Because it breaks the limits of physical RAM. One of the key ideas here is that programs don't work with physical memory addresses directly. Instead, they create what's called a virtual address. This virtual address acts like an alias, a layer of abstraction between the program and the actual hardware. The system then translates this virtual address into a physical one behind the scenes. This separation is crucial. It helps with security, flexibility, and efficient memory management. Understanding this difference is fundamental to how modern computers handle memory. Let's break down how memory addresses work in a computer. First, we have the virtual address. This is generated by the CPU. It's like a label or a reference point. Then, there's the physical address. That's the actual location in the RAM where data lives. The key player here is the Memory Management Unit, or MMU. Its job is to translate the virtual address into the physical address, making sure the CPU accesses the right spot in memory. This translation is crucial for efficient and safe memory use. Let's talk about how virtual memory works in practice. Instead of dealing with one big chunk, memory is split into fixed-size units called pages. These pages can be loaded into any available physical frame in the actual hardware. Think of pages as virtual slots and frames as the real spots in memory. This system gives us flexibility. It lets the operating system manage memory more efficiently, swapping pages in and out as needed without worrying about their exact physical location. Here, we see an example of how virtual pages are mapped to physical frames in memory. Each virtual page corresponds to a specific frame, but not necessarily in a sequential order. This mapping is managed by the page table, which the operating system maintains. The page table acts like a translator, keeping track of where each virtual page lives in physical memory, ensuring that the system can find data efficiently and correctly. Let's break down what makes up a virtual address. It's split into 2 parts, the page number and the page offset. The page number points us to the specific virtual page we want to access. Meanwhile, the offset tells us the exact spot within that page. When translating addresses, the page number helps us look up the page table, but the offset stays the same. This structure is key to how virtual memory works behind the scenes. Let's think about how we translate page numbers into frame numbers. The key idea here is that while the page number changes, the offset stays the same. This means we're shifting our reference point without altering the baseline. It's a simple but powerful concept. Keeping the offset constant lets us map pages to frames smoothly and accurately. This approach keeps everything aligned, making the process more predictable and easier to manage. So, what happens when the page we need isn't already in RAM? That's what we call a page fault. It's basically the system's way of saying, "Hold on, I need to fetch this data first." When a page fault occurs, the computer has to pause and load the required page from slower storage into RAM before it can continue. This process is critical to how virtual memory works, balancing speed and capacity behind the scenes. When RAM is full and a page fault happens, the operating system has to make room by removing a page already in memory. This process is called page replacement. There are a few common algorithms for deciding which page to remove. FIFO, or first in, first out, kicks out the page that's been in memory the longest. LRU, least recently used, removes the page that hasn't been accessed for the longest time. And the optimal algorithm, which is more theoretical, removes the page that won't be needed for the longest time ahead. Every time a program accesses memory, the processor needs to translate virtual addresses to physical ones. Doing this by checking the full page table each time would be too slow. That's why processors use a small, superfast cache called the TLB, the Translation Look-Aside Buffer. The TLB stores recent address translations, so the processor can skip the slow lookup and keep things moving quickly. It's a clever shortcut that speeds up memory access dramatically. Let's talk about how the Translation Look-Aside Buffer, or TLB, works. When there's a TLB hit, it means the translation we need is already stored there, so things happen faster. But if there's a TLB miss, the translation isn't found in the buffer. That means the system has to check the page table, which takes more time. This simple hit or miss process has a big impact on overall performance. Let's talk about the virtual memory system, a key concept that lets computers use more memory than they physically have. It creates an illusion of a large, continuous memory space by swapping data between fast RAM and slower storage. This system helps programs run smoothly, even when memory demands are high. Understanding how virtual memory works gives us insight into how computers manage resources efficiently behind the scenes. Virtual memory brings several key advantages to the table. First, programs larger than the available RAM can still run, because they don't need to be fully loaded at once. This leads to better memory use. Only the parts a program actually needs get loaded. It also keeps processes isolated, giving each one its own virtual address space. That makes development easier, since programs don't have to worry about where physical memory lives. And finally, virtual memory supports multitasking, letting multiple programs share memory smoothly and efficiently. Page faults come with a real cost. When our system has to reach out to the SSD or hard drive, it's much slower than grabbing data straight from RAM. If page faults happen too often, the system can get stuck in a loop called thrashing, constantly swapping data in and out, and slowing everything down. This is a major disadvantage we need to watch out for when managing memory effectively. Thrashing happens when a system gets stuck shuffling data back and forth between RAM and secondary storage, instead of actually running programs. When this takes over, the CPU ends up waiting around, doing less useful work. The result? CPU utilization drops, and overall system performance tanks. It's like the system is busy, but not productive. Understanding thrashing helps us see why memory management is so crucial for keeping things running smoothly. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about direct memory access, or DMA. It's a clever technique that lets input-output devices send data straight to or from the main memory, the RAM, without needing the CPU to manage every single byte. This means the CPU can focus on other tasks, while data moves efficiently in the background. DMA speeds things up and reduces the CPU's workload, making the whole system run smoother. It's a key part of how modern computers handle data transfers. Let's take a look at the basic architecture of DMA, direct memory access. This system lets devices transfer data directly to and from memory, bypassing the CPU. That means less work for the processor and faster data movement overall. We'll break down the key components and how they interact to make this possible, setting the stage for a deeper dive into DMA's role in efficient computing. Every time data moves in a computer, the CPU is involved. In normal input-output operations, the CPU handles each step, reading, writing, and managing the data transfer. This means the CPU is tied up, busy moving data instead of doing other work. Without DMA, or direct memory access, the CPU becomes a bottleneck, limiting overall system efficiency. This slide sets the stage for understanding why DMA is such a game changer. The DMA controller takes charge of moving data directly between devices and memory. With DMA, the CPU doesn't have to get involved in every single transfer. It frees up processing power and speeds things up. Instead of the CPU shuffling data byte by byte, the DMA controller handles the heavy lifting, making data transfer more efficient and smoother overall. This is a key part of how modern systems keep things running fast and responsive. Let's break down how the CPU kicks off a DMA transfer. First, the CPU sets the starting memory address, where the data will go or come from. Then, it tells the system how many bytes or words need to move. Next, it specifies the direction of the transfer, whether data, going to or from the device. Finally, it provides details about the I/O device involved. These steps set the stage for DMA to take over and handle the data movement efficiently. Now, let's look at how DMA takes over the bus to move data efficiently. First, the DMA controller requests control of the system bus. The CPU then temporarily hands over the bus to DMA. This lets DMA transfer data directly between the I/O device and RAM without involving the CPU. Once the transfer finishes, DMA sends an interrupt to the CPU, letting it know the operation is complete. This process frees up the CPU to focus on other tasks, while data moves seamlessly in the background. Let's take a closer look at the key registers inside a typical DMA controller. First, the address register. It holds the memory address where data will be read from or written to. Then, the count register. This keeps track of how many bytes or words need to be transferred. The control register specifies what kind of transfer operation is happening. And finally, the status register. It tells us the current state of the DMA, whether it's busy, complete, or if there's an error. These registers work together to make direct memory access smooth and efficient. Let's look at 3 common modes for DMA transfers. First, burst mode. Here, DMA grabs the bus and moves a large block of data all at once. It's fast, but the CPU has to wait longer because it can't use the bus during that time. Next, cycle stealing. DMA and the CPU take turns using the bus, transferring one piece of data at a time. This way, both share the bus more fairly. Finally, transparent mode. DMA only transfers data when the CPU isn't using the bus at all, so it never interrupts the CPU's work. Each mode balances speed and CPU access differently. When it comes to moving data around, there are 2 main approaches: programmed I/O and DMA. Programmed I/O keeps the CPU deeply involved, controlling every step, which slows things down and adds overhead. DMA, or direct memory access, takes that burden off the CPU, letting data transfer happen faster and more efficiently. Especially with large data transfers, DMA shines, handling the heavy lifting while the CPU focuses elsewhere. This comparison highlights why DMA is often the better choice for performance. An I/O interface acts as the bridge between the CPU and external devices like keyboards, printers, or network hardware. It's responsible for moving data back and forth, sending control signals, and keeping track of status information. Most importantly, it makes sure the CPU and these devices stay in sync, so everything runs smoothly without any hiccups. This interface is essential for seamless communication within the system. Let's talk about parallel interfaces. Here, multiple bits move at the same time, each on its own data line. So if you have an 8-bit parallel interface, you're transferring 8 bits all at once. This makes data transfer faster compared to sending bits one by one. It's like having several lanes on a highway instead of just one. More cars can go through simultaneously. This approach is common when speed is key and the hardware supports multiple lines working together. Let's look at an example to understand this better. Imagine we have the data 10,110,110. All 8 bits can be sent at once. This means a high data transfer rate, especially over short distances since multiple bits move together. But there's a trade-off. It needs more wires, which makes it more expensive. Plus, keeping signals synchronized gets tricky as the distance grows. So it's a powerful method, but with some practical limits. Let's break down the key differences between parallel and serial interfaces. Parallel transfers multiple bits at once, using more data lines, which makes wiring complex and costs higher. Serial, on the other hand, sends one bit at a time, with fewer lines, simpler wiring, and lower cost. When it comes to long-distance communication, serial is more suitable. Think of a parallel printer interface versus USB or UART. That's the practical side of these two approaches. With interrupt I/O, the CPU isn't stuck constantly checking if a device is ready. Instead, the device takes the initiative. It sends an interrupt request to the CPU when it needs attention or when a task is done. This way, the CPU can focus on other work and respond only when necessary, making the whole system more efficient. It's a smarter way to handle communication between the CPU and I/O devices. Let's talk about programmed I/O here. The CPU keeps checking the device status over and over. This constant checking is called polling. The problem? The CPU ends up wasting a lot of time just waiting and watching, instead of doing other work. This approach contrasts with interrupt I/O, where the device signals the CPU only when it needs attention. Understanding this difference helps us see why programmed I/O can be inefficient in many situations. When the CPU can perform other tasks while waiting for input or output, it's working more efficiently. Instead of constantly checking if something needs attention, the CPU gets notified only when it actually does. This approach, called interrupt-driven I/O, frees up valuable processing time and keeps the system running smoothly. It's a smarter way to handle communication between the CPU and devices, making sure resources aren't wasted on unnecessary waiting. Let's talk about what happens when we interrupt an input-output operation. This sequence is all about pausing or stopping a process that's waiting on data, maybe from a disk or a network. Interrupting I/O lets the system regain control, handle other tasks, or respond to urgent events. It's a key part of keeping everything running smoothly, especially when delays or errors pop up during data transfers. An interrupt service routine, or ISR, is a special kind of code that the CPU runs whenever an interrupt happens. Think of it like an urgent message that demands immediate attention. For instance, when you press a key on the keyboard, the CPU pauses what it's doing and jumps to the ISR to handle that input quickly. This ensures the system responds in real time, keeping everything running smoothly. Both interrupt-driven I/O and DMA help cut down on unnecessary CPU work, but they do it in different ways. Interrupt I/O involves the CPU more. It handles transfers through its registers and gets notified during or right after each I/O event. DMA, on the other hand, takes control away from the CPU almost entirely, moving large blocks of data directly between memory and the device, and only alerts the CPU once the transfer is done. Each method suits different needs, depending on transfer size and timing. To wrap up, let's remember the simple distinction between interrupt I/O and DMA. With interrupt I/O, the CPU gets a direct call for attention. With DMA, the data moves on its own, and the CPU only hears back when the job's finished. It's a small difference, but a powerful one.
Thank you for watching my video. Please do like, share and subscribe my channel for more videos.